You know what he is famous for? He gave us a principle with regard to pushing the equilibrium reactions out of their equilibrium status and how they return. So everything that we do to an equilibrium reaction, it will try to annul what we have done. We have seen that. And apparently I didn't know this, but the Sharpley principle is also there in economics. The same principle. Yeah. Do anything to the market to push it away, to try to annul that effect. So if you try to increase the cost, the demand goes down. And therefore, so I believe. But of course, most people who teach you the Sharpley principle will keep telling you that human behavior is the Sharpley oriented. If I tell you not to talk, you will talk. But if you talk, you will not talk. Stop that. Well, if I ask a few people out here to come and talk here, they won't talk. But if they don't talk, you will sit there and talk. I think the Sharpley principle is much more deep-rooted than just being used for equilibrium reactions. 11th is Friedrich Bergius. Friedrich Bergius was a Nobel laureate in 1931 in chemistry, and what he essentially did was he produced synthetic fuel from coal by essentially using high pressure, high temperature reactions. So we just take coal and any of the coal tar products or whatever and keep them at very high pressures and temperatures. You essentially produce hydrocarbon-like fuels. These are synthetic fuels that he produced and marketed, and that was quite important from the point of view of energy sources. He actually, I think, worked with Haber, with Frisch Haber, and the Haber process for ammonia and so on. He had his contribution. His name doesn't show up, but he had his contribution till there. And he was somebody who worked with high temperature and high pressure reactions. Today, of course, when you talk about high temperature and high pressure reactions, earlier high pressure reactions meant a few bars. Today, anybody who says I'm doing high temperature and high pressure reaction, and if you tell him, look, what's the pressure, and you say like 3 bar, 10 bar, 20 bar, he'll say that's all. So that's not good enough pressure. Today you speak about kilopascals, megabars, and gigabars, by using diamond angle cells. You take a compound, put it between 2 diamond pieces, and then you squeeze them through. And diamond being as hard as you can think of. As hard as it can be, you can actually produce pressures like in the realm of many megabars and higher. So essentially, you're looking at reactions that can be conducted at extremely high pressures, and all sorts of weird chemistry goes on under those conditions. And now what people have done is they take these high pressure diamond angle cells. Of course, diamond is the only thing you can use because nothing else will beat it in terms of hardness. And it's also transferred as a nice thing. So you can pass a infrared laser through it onto the sample which is being squeezed. Now the infrared laser would actually heat it up, and when you heat it up with an infrared laser, you can get temperatures like 2,000–3,000 Kelvin. So you now put material at megabars and temperatures like thousands of Kelvin, and you can then see that none of your rules of chemistry which you are used to at room temperatures will never work over there. It's all completely free for all at that point. Anything goes. If you take carbon, for example, and put it under the diamond angle at high pressures and leave it for a while, you'll get damaged because of the pressure and temperature. Very similar to what happens in the Earth's crust. So many people who do these reactions are actually looking at trying to mimic subterrestrial situations or things like what happens, what exists in Jupiter and so on, where the pressures are very high, temperatures are very high. And these things are something that people look at. So that's Friedrich Bergius for you. 14 was Edward Deming. I could never find a chemist or a physicist who was born. Maybe one of these two must become famous soon, so that's fun. I didn't get you at all. Oh, on 14? Yeah. Oh, good. Then he's got something. So I think he's probably on good up. It's good. Can you do that? See, the only reason I'm doing this is because there are two things. One, you always feel nice to share it with somebody big, and plus you learn something as an excuse, in going through all this, which is something that you might not otherwise learn in the class. Edward Deming is a statistician, and apparently he brought in a lot of new concepts in statistics, and both in terms of statistics as applied to physics, and chemistry, and also statistics applied to economics again. And 1710 was Kolesnikov, who was a Russian physicist and who had a lot of contributions to make as far as relativistic issues were concerned, and particularly for astronomical purposes. So these are the 4 people that I actually came up with. Today it's actually Kroto and also Niels Bohr. Yeah, so Niels Bohr's birthday, of course. Unfortunately, he's not allowed to visit the track. Kroto is today. I just told Shweta, Shweta has met him and they practiced with him. And I told her, look, it's Kroto's birthday tomorrow. There's time. Now that she told me I can send him a birthday note or something. Of course, you can't send one to Bohr, but at least you can send one to Kroto. Of course, there's no need to talk about who Bohr was and so on. I don't want to bore you with that. Okay, what I will do is I will put up some 3 problems and just solve it for yourself. I'm not going to correct it, I'm not going to give you marks for it. It's essentially a sort of a practice I'm giving you. Oh, but again, don't please assume that these are part of the exam questions or something. I'm not still set your paper yet. Okay? So don't be carried away. It's just a practice on how to handle these problems. Do it by yourself. Do not consult. If you consult, you're hurting yourself at the end of the day because you still don't know whether you know the answers or not. So don't do that. Just answer it for yourself. I'll give you about 15 minutes. We'll come back and quickly go through the answers for that. what you have to do with the drawing is I've just shown some transitions. And you have to tell me whether the transitions are going to be allowed or not. And if they are not going to be allowed, you must be able to say why they are not allowed. If you say they are allowed, then of course there is no issue. It's allowed. That means all the selection rules are obeyed. But if you say it's not allowed, then you must tell me which selection rule it is that it is violating and why the transition is not allowed. I think the V1 is simply going to the ground state. 1 has to do that. But everything else you can see. I don't even worry about the B transition. If you know the others, you will know how to do B. You just forget B. Do A, C, D and E and tell me whether they are allowed or not. And if they are not allowed, tell me why they are not allowed. That's the third question. The second question is about carbon dioxide normal modes. And the first one is something very similar to what I treated just a little while ago. Do work out the problem completely, even if you think you know it.
Today we'll shoot, record them.
del L. What I will do in a few minutes is, without giving you the answer, I will go through the way that you must solve it. I will then send this over to email to all of you. That if you haven't completed it now, still try to work on it later on and see whether you can come up with all the answers. Let me start from the third one and tell you quickly how to go about that. Okay, what about transition A? Is it allowed or not allowed? It's allowed because it's P to D, therefore little L changes by one quantum, therefore it's okay. Spin is the same because they're both single state, is one half of the table, is on that side. It's not switching from singlet to triplet. It's actually a transition from a triplet P to a singlet P to a singlet D. Right? It's going from a singlet the A actually goes from here to there. It is a singlet P state. These are all singlet D states. So it's going from a singlet P to a singlet D. Therefore, spin is conserved. Delta S 0, that's no problem. What about the electron? It's a 2p electron going to a 3d electron. So little l has changed by 1. That's okay too. A capital P has gone to capital D and therefore delta L is 1. That's fine too. And what about J? J has gone from 1 to 2, which is also fine because you can have a delta J of plus minus 1 or 0. So you'll find that A has all the selection rules obeyed and therefore the A transition will actually be seen in the spectrum. There's no problem with that. What about B? And what is it violating straight away? It's violating a few things actually. It's violating the little L selection rule because S is going to D. And what else? The capital S is going to capital D. Delta L is also 2. Therefore it's actually, and what about S? J? J0 is going to J2. And therefore it's actually violating about 3 different selection rules. You're not going to be able to see this transition. If I give you a problem like this, you have to give me every selection rule that it violates. Don't stop with one. Say that look, delta L is not plus minus 1. Therefore it is not going to happen. So why do I bother about the others? Well, in real life, you don't have to bother about the others, but in exam, you have to bother because I want to know whether you got everything correct, whether you got all your concepts right. So you got to tell me all the selection rules when it actually violates. What about C? C basically violates the delta L selection rule because the spin has changed from a singlet to a triplet. Everything else seems fine, excepting that it's going to have a problem with respect to its spin between the two states. So a singlet going to a triplet is actually crossing the barrier, the dotted barrier. And if it crosses the dotted barrier, I'm actually going from singlet to triplet or vice versa. And that can't be allowed, and therefore that transition is not going to be possible. What about D? D is actually an S going to a P, little n is okay. It's a triplet S going to a triplet P, that is okay. It's a capital S going to a capital P, that is okay. But what about the J? Yes, there is 1, starts from 1 over here and is going to 0 up there. And why is it 0? I didn't put a label 0 up there. How do you know it's 0? Yes, it's a half fill, therefore the lowest J has to be the lowest in energy. Therefore, you don't have to tell me that, because I didn't put J equal to 0. So how do you know it is J equal to 0? You know it's J equal to 0 because it's less than half full. Therefore, the lower J has to be the lowest in energy. And therefore, that's fine. What about E? E is not going to be allowed simply because it's a delta L not changing and therefore it's basically. And what about anything else that is not, that's a problem? J is 0 for the start. And what's the top one out there? J is 2. Therefore, you're going from 0 to 2. And therefore, the delta J transition is also going to be disobeyed. Therefore, you have a delta L selection rule and the delta J selection rule. That's going to be important. So, you got to, this is what I'm looking for. You must tell me all the selection rules that are. Of course, if you say it is obeyed, you don't have to tell me delta S is obeyed, delta I assume that if you say it is obeyed, the transition is possible, that all selection rules are taken care of. But if you say it is not possible, you have to give me all the selection rules that you think have been violated. Let's go to the second problem. And there are quite a few things inside there. It says carbon dioxide has normal modes of vibration with frequencies 2349, 1350 and 667 wave numbers. I haven't told you what these modes are, but that's not important. But you know what these modes are. The 2350 has to be the 2349 has to be the highest frequency is generally the antisymmetric mode. So it's this mode. It's the carbon dioxide. One oxygen carbon bond shrinking while the other one is expanding and vice versa. The 1350 is the symmetric stretch. And the third one, 667, which is pretty low in wave number, has to be the bend. Because it's always easier to bend a molecule than to stretch the molecule. So bending vibrations will generally be of low frequencies compared to stretching vibrations. That's the assignment as far as the normal mode picture is, or the vibration picture is concerned. But you really don't even need to know this to answer this question. What does the question say? It says the first and the third are observed in the infrared spectrum and correspond to the antisymmetric stretch and the dominating net bend, because I have given you that. If CO2 is irradiated with neodymium laser, there is a frequency of 1064, that's wrong, it's actually a wavelength of 1064 nanometers, not frequency. To obtain a vibration Raman spectrum, what would be the frequency of the scattered radiation that you will observe in the Stokes region? So, what are the issues in this? I already told you that 2349 and 667 are observed in the infrared spectrum. This molecule has a center of symmetry. Therefore, those will not be seen in Raman. So you got to tell me that first. If you blindly just calculate the Stokes scattered radiation for every one of those vibrations, mind you will lose marks for telling me that you will see a scattered radiation corresponding to 2349. So because 2349 is an infrared transition, molecule has a center of symmetry. Therefore, you cannot see it in Raman. We know the principle of mutual exclusion, and that's what I'm trying to probe in this. So if you give me the scattered radiation corresponding to 2349,